right, we're going with the advanced questions for AP Physics 1. This is on energy and conservation. It is number 4 under the more advanced questions. It says a spring, got some surface like that, there. Boy, you can barely see that. So there's a spring over here and a box pressed up against the spring, has a mass of 5 kilograms. Great. And again, here's the surface. That. All right. It says the spring constant is 7,500 newtons per meter, 5 kilogram box, and it is pulled back a distance of 20 centimeters. Okay, that's important because that kind of tells us how much energy is stored in the spring. So for those of you who need it kind of spelled out for us a little bit, you pull the block against the spring stores energy. You release the block from the spring pushes the block, doing work on the block. When it does work on the block, it changes its kinetic energy. The block then can slide away from the spring. It's going to slide up the ramp. As it goes up the ramp, it's going to convert that kinetic energy into a different kind of potential energy. This time it'll be converted into gravitational potential. So we're going to actually answer the questions that are there. Question A says, how much work is done on the spring when the box is pulled back 20 centimeters against it? The work done on the spring. It would be hard for you to probably answer this one if you didn't recognize that doing work on the spring is storing energy in the spring. And that energy is stored in the form of elastic potential energy, which means that the elastic potential energy in the spring represents the work you did in compressing the spring. That'll be 1/2 times K, which is 7,500, times the distance you pull it back squared, but that has to be in meters. So 0.2 squared. This gives us a total amount of energy of 150 joules. Hold on to that number. Assuming that there's no losses due to friction, then 150 joules is the amount of energy in the system. Right now stored in the spring. That was the work we did compressing the spring. Question B, how much elastic potential energy is stored in a spring? Well, that's the answer to question B too. 150 joules is the work done on the spring. Question C, assuming the floor and the ramp is frictionless, how fast is the block going after it leaves the spring? Assuming the floor and the ramp is frictionless, well, let's see, I'm going to draw a little bit of a picture right here below the ramp. There's the spring pressed against the block, and then there's the block separated from the spring and scooching off to the right at some velocity. Here, I'll have all elastic potential, but that's all going to be converted into kinetic in the block. So if I want to find out how fast the block is going, it's probably best to figure out how much kinetic energy there is in the block. Well, since the energy is conserved, the 150 joules of energy that was elastic is now 150 joules of energy that is kinetic. The block has a mass of 5 kilograms. I think I can use this now to figure out how fast the block is going after it leaves the spring. So it'll be 150 equals 1/2 times 5 times v squared. So let's see. That's v squared equals 60. Pretty sure that's 60. So v is going to be square root of 60, which is 7.75 meters per second. All right, this problem is going by just fast. If the ramp is 0.5 meters high, all right, so they're saying this part of the ramp is 0.5 meters high. Then, how fast is the block traveling when it makes to the top of the ramp? All right, so question D. Let's consider that real quick. I'm going to draw the ramp yet again, and I want to compare the amount of energy the block has right there with the amount it had. Well, I can go all the way back to when it was against the spring. Energy's conserved. So here, and way up there, those 3 places, I have elastic when it's against the spring. That was converted into kinetic when it's on the flat portion of the the ramp. And then, when it makes it up here, it's going to have gravitational potential because it's above the reference level. And if it's still moving, if there's any energy left over, it'll all fall into kinetic. Well, the important thing, it's 150 joules here, 150 joules here, and 150 joules here. The energy is conserved. So, for question D, I have 150 joules equals the gravitational potential energy plus the kinetic energy of the block. That's going to be 150 joules equals the mass times g times the height of the block plus 1/2 mv squared of the block. So that will be 150 joules equals 5 times 10 times 5. That is the gravitational potential energy of the block. Oh wait, it's not 5 meters high. Silly me. It's 0.5 meters high. All right, good enough. So plus 1/2 times 5 times v squared. So let's go ahead and do a little bit of algebra here. I'm just getting all this stuff out of my way. And I'm going to have 150 equals, let's see, 5 times 10 is 50, times 0.5 is 25, plus half of 5 is 2.5 v squared. All right, let's subtract that 25 from both sides. I'll get 125, 250, I think it's going to be 50. I think it's going to be 50. But let's just check. 150 minus 25 divided by 2.5. 140, I don't think so. Yeah, I was right, 50. V squared equals 50, which means the velocity, when I make it right there, that velocity is going to be the square root of 50, which is about 7 meters per second. So I would say that that block is still moving pretty fast. Don't put your face there, ladies and gentlemen. You'll get it broken off. All right. Wow, that's question D. I still have E, F, and G. E. The box leaves the ramp traveling straight up. What is the maximum height achieved by the block? So, all that, consider that the block keeps going up. I'm kind of out of space here, so let's grab another page. All right, so we had the block here against a spring, had 150 joules of elastic potential energy. The block then left the spring. It had 150 joules of kinetic energy. It made it to a point that was half a meter off the ground. It still had 150 joules of energy that was both gravitational potential and kinetic. And now it's going to go all the way up to a point where it comes to rest. Since it's going to come to rest, I don't know how high it is, some height off the ground, but I do know that it will only have gravitational potential energy because it's not moving. But it's still got 150 joules of energy. Unless there's friction or something to take the energy away, the energy is conserved. So for question E, the gravitational potential energy equals 150 joules. That's mgh equals 150 joules. That's 5 times 10 times h equals 150 joules. So h equals 3 meters. When the toy is actually created, this is question F. All right, question F. When the toy is actually created, it is impossible to eliminate all the friction. When the box is launched, it only makes it 2.5 meters at its maximum. How much work was done by friction? All right, this sounds like a lot harder problem than it is. When the box is actually launched, the height is 2.5 meters, not 3. So, some energy was lost due to friction. Well, how much energy does it have? If it makes it to a height of 2.5 meters, then it has gravitational potential energy based on being 2.5 meters above the ground. The mass was 50, G is 10, H is 2.5. It did not make it 3, it only made it 2.5. So if we want to figure out how much energy it has, just multiply that out. We find out it has 125 joules of energy. Now listen, it had 150 joules of energy when it was in the spring. After sliding along the table, friction took some energy away. The block only has 125 joules remaining. How much work do you think was done by friction? Well, I bet it was the amount of energy lost. Right? It had 150 joules when it was against the spring. When it's in the air, it only had 125. I think friction took away 25 joules. And you're asking why it's negative. That's because me being so silly, didn't think to put final minus initial. So let's do it that way. Let's look at the energy final minus energy initial. The final energy was 125 joules minus the initial energy, which was 150 joules, which means negative 25 joules. That was the work done by friction. It took away 25 joules. G, if a more massive box is used instead, how will this affect the height achieved by the launcher? It will be lower. The amount of energy stored in the spring is not dependent on the mass. The amount of energy stored in the spring is dependent on the spring constant and how far back you pull it. That amount doesn't change. However, how high it goes does depend on the mass. Gravitational potential energy is based on how massive the object is. So if you make the object more massive, it can't go as high. Moreover, there's going to be more friction, likely slowing the box down more. So the answer to that question is it won't go as high. There you go, that's question number 4. It is definitely a more challenging question. That, my friends, represents what I think you should be able to do on your test.